Hey guys, good morning. Thanks for joining us. Like I said, we are going to keep going. So yesterday we kind of learned the process of dimensional analysis. Sorry, I have more people popping in from the lobby. We learned the process of dimensional analysis of how to set up problems, allowing our units to cancel out to change our unit of measurement. So we're going to be using that same process kind of moving forward, but we're going to be doing it with chemistry terms. My guys at home, you do need access to a calculator, whether you pull one up or have a handheld one, and a periodic table kind of close by or handy. So we are going to go ahead and start off. This will be kind of a longer note day. We'll get done before the live time, but just kind of preparing you. It's just one of those things that there's not really a good stopping point anywhere before then. So we're going to be talking about measuring matter. So remember, matter is anything that has a mass and takes up space. So everything is considered matter. We're going to look at matter in terms of the count or quantity of a substance. So we're particularly going to look at particles of a substance. So how many particles or atoms there are of a different substance. We're also going to look at matter in terms of mass, so grams. And we're also going to look at matter in terms of volume or liters. So our focus today is we're going to be focusing more on the particles and the grams today. And we're going to add in the volume tomorrow and do some multi-step problems as well. So if it'll go, there we go. A unit that we're going to be dealing with that you've probably never heard of before is the mole. A mole is a bulk unit. So kind of like if you're going to the store and you need 24 eggs, you're not going to go and literally pick out 24 eggs. You're going to buy 2 dozen. A dozen is a bulk unit that's equal to 12 eggs. That's kind of a common bulk unit that we use. Same thing if you were going to buy computer paper. Whenever you go buy a pack of computer paper, that is a ream of paper. That's 500 sheets of paper. So instead of counting out 500 sheets of paper, you just buy one ream, one pack. So a mole is going to be a bulk unit just like that, because since particles are so small. So way back in Unit 2, we kind of introduced the atom and said they're so small that if you lined 1 million atoms up in a row, that would be about the width of your pinky. That's how small they are. So because they're so small and there's so many of them, it's going to be really hard to count individual atoms or particles. So we use the mole as a bulk measurement to discuss how many particles there are. So a mole is going to be an amount equal to 6.02 times 10 to the 23rd representative particles of a substance. So 1 mole is 6.02 times 10 to the 23rd particles. So that 6.02 times 10 to the 23rd particles is Avogadro's number. That's going to be used as a conversion factor for us. So where someone asked yesterday, are there certain numbers we have to know and use? Yes. So this is one of them. But it is on your reference sheet. So it's not a number that you have to memorize. You just have to be able to use it. So kind of navigating where it is on your reference sheet, the very first page of your reference sheet that says the chemistry reference tables, it's the very first thing that's listed on that left side. So it's Avogadro's number, and it tells you it's the 6.02 times 10 to the 23rd particles per mole. So this is going to be a constant for us. No matter what substance we have, 1 mole of that substance is always going to have that 6.02 times 10 to the 23rd particles. So like I said, you don't have to memorize it. You probably will because you're going to be kind of using it repetitively. But it's on your reference sheet. You just need to be able to use it appropriately whenever we get to do conversions. Like I said, bear with me. I'm trying to make sure everybody can write, but if I'm missing somebody and going off and leaving you, let me know. So looking at what is meant by representative particles. So representative particles, there are different types of particles that exist. They're all going to have the same number in a mole, but different terms might be used to express different types of particles. So if you see atoms, this is going to refer to the individual particle, the smallest piece of an element. So anything right off the periodic table, like iron, sodium, sulfur, anything like that, is going to be represented as atoms as the individual particles. You might also see the term molecules. So molecules are from molecular compounds. So remember, molecular compounds were between nonmetals only. So anything that's nonmetals combined, the smallest particle will be a molecule. So these are going to be our molecular compounds and our diatomic molecules, because remember we have those elements that were in Brinkelhoff that are never by themselves. So this might be something like hydrogen gas because it's H2. It could be silicon dioxide, carbon dioxide, water, oxygen gas, because yet again it's that O2 and not just O. And then you might also see formula units. This term isn't used as often as the others, but formula units are the individual particle, the smallest piece of an ionic compound. So remember, ionic compounds were between a metal and a nonmetal. So this might be something like potassium chloride, table salt, lithium hydroxide, silver nitrate, barium chlorate, anything like that that has a metal and nonmetal. The smallest particle is going to be a formula unit. So anytime you see particle, atom, molecule, or formula unit, they're pretty much all interchangeable. You're still going to be doing the same conversion no matter what term is used. And a mole of any substance contains Avogadro's number, that's 6.02 times 10 to the 23rd particles. So 1 mole of an element is going to be the 6.02 times 10 to the 23rd atoms. 1 mole of a molecule will be 6.02 times 10 to the 23rd molecules. So kind of going back and forth. So like I said, that Avogadro's number is going to be used as a conversion factor for us. So we're going to be able to do the dimensional analysis process and cancel out units using that conversion factor. So the conversion factor for particles is that 1 mole of anything is equal to that 6.02 times 10 to the 23rd particles. So since those two are equal to one another, that can be used as a fraction, as one of our conversion factors to allow us to cancel out units. So just like we did yesterday, where you had that conversion factor of two things that were equal, and that unit either went on the top or bottom, depending on what you were trying to cancel out. So here's an example of how this will be used to convert from particles to moles or moles to particles. We can go either direction. So our example here says that magnesium is a metal used in the manufacture of aircraft, automobile wheels, tools, and garden furniture. How many moles of magnesium is going to be 1.25 times 10 to the 23rd atoms of magnesium? And sometimes you'll come across problems that have like extra stuff in there. So that whole first sentence is just extra stuff that you don't necessarily need. But you want to figure out what you actually have to start off with and what unit you're trying to convert to, what unit you're trying to change into. So with this one, it wants to know how many moles, and it tells us we're starting with 1.25 times 10 to the 23rd atoms. So that number that's given is going to be the beginning of our conversions. And feel free to like abbreviate the units and stuff, but make sure every number should have a unit associated with it. Now we're trying to change into moles. So setting up like yesterday, atoms right now was given, so that's on top. So where should that unit go in our next factor for us to be able to cancel it out? Yeah, on the bottom. So remember, you want the unit on top somewhere and on the bottom somewhere else. So atoms is going to go to the bottom. And we can go straight from atoms to moles. That's a conversion factor. So that's what's given. So our conversion factors are always going to be based off of 1 mole. And 1 mole is that 6.02 times 10 to the 23rd atoms. Now I want to start with this one. So this is going to allow atoms to cancel out, and it gives us moles. So we're done with our setup. We just have to put in the calculator. A lot of times the hardest part of these is putting them in the calculator because we have those numbers in scientific notation. So one option that you have whenever you're putting the calculator is to put both of these numbers in parentheses. So remember, since this is on the bottom, you're going to be dividing by that 6.02 times 10 to the 23rd. So make sure if you type it in that way using parentheses, make sure that you open and close each parentheses. There is another way to type in numbers with scientific notation in your calculator. Yeah, somebody's trying to pop in. There we go. So the Mg underneath is the magnesium. That's just the symbol of what we have. So that came up on the side. So the other way to type this in the calculator is all calculators, at least if you have a TI calculator. Some people might have Casio and stuff. They have the buttons. I'm just not sure where they are. I'll have to find them. But all calculators have this EE button. On TI calculators, it's a second function. So it's going to be second, and it's the button above the 7. It's the second comma is an EE button. That EE takes the place of times 10 caret. So that's what that function is. That whole button is times 10 caret. So that takes out 4 buttons that you have to hit whenever you're typing it in. So like I said, you can type it in as is using parentheses, or you can use this EE button. If you use the EE button, you don't have to use parentheses, and it saves you a couple buttons that you have to hit. But how you would type this in is you're going to have the coefficient. So we would type in that 1.25. Hit the second EE button, and it pops up a single E on your screen. And then all you have to type in is your exponent. So the 23. And then we are dividing by. And for our other number, use your coefficient, the 6.02. Hit the second EE button, and then type your exponent, the 23. So either way you type it in, you should get 0.208 moles of magnesium. Now, here's where I said the hardest part is typing it in. A lot of people will show their work correctly, but type in the calculator wrong, and it gives them a wrong answer. But that's kind of the importance of showing your work, because if I can see that you set it up correctly, but your answer's wrong, how we kind of score this stuff is each conversion, each step is worth a point, and then the answer's worth a point. So if you messed up just one thing, you don't lose all the points for the question. You only lose that 1 point. You still get all the other points for using it correctly throughout the rest of the process. So if you did not get that answer, I'd check and see how you typed it in. Did you make sure to close your parentheses? Or does it appear, if you use the EE button, does it appear exactly as it is up here? So the setup's not the hard part, punching the calculator is the hard part. All right, let's look at one more with particles. So this one was going from particles to moles. Let's go the opposite direction. This one wants to know how many molecules are in 0.360 moles of water. So we're looking for molecules. That's what we're trying to convert to. And it gives us the 0.360 moles of water. So that's what we're going to start with. And they abbreviate moles just as MOL. They just knock off the E. So you'll see it either with an E or without an E. So we're trying to go from moles to molecules. So we no longer need moles. So where would that unit go in our next step? Yep, on the bottom. And we can go from moles to molecules. Make sure to abbreviate moles and molecules separately. That way you don't confuse what you actually have. Remember we said moles is always going to be 1. And molecules in a mole is that Avogadro's number. That's 6.02 times 10 to the 23rd. So that's going to allow the unit of moles to cancel out. And since both numbers are on top, we're multiplying them. So remember your number in scientific notation, you either want to put it in parentheses or use that EE button, whichever one you prefer. So we're going to do the 0.360 times the 6.02 times 10 to the 23rd. And we're going to end up with about 2.17 times 10 to the 23rd molecules of water. So if you punch this in your calculator, like it probably gives you like 2.1672 E23. So remember that E is the times 10 caret. So you still need to write the times 10 to the 23rd as part of your answer. So I do have more examples with molecules, but are y'all feeling okay? All right, do we need to do any of the other molecules examples or keep moving? I'm gonna take silence as you're good. Yep, okay. So let's move on. So that's all the conversions with particles. It's just using that same conversion factor that's always a constant, just figuring out should that number go on the top or on the bottom of our conversion factor. I don't know what just happened. Here we go. All right. So let's skip ahead and look at mass. So mass are probably the hardest conversions because it's not going to be a set constant for everything. So it's not always going to be the same number that we're going to use for mass. So on your periodic table, remember the square on the periodic table has your atomic number, your symbol, your name, and then that number at the bottom, which is your average atomic mass. So that mass on the periodic table, where we dealt with it back in Unit 2, was measured in AMUs or atomic mass units. We can also use this number as grams, and this is going to be grams per mole. So what is listed on your periodic table is how many grams, the mass of 1 mole of that element, which is going to be our molar mass. So molar mass, our conversion that we're going to be using, is straight off of your periodic table. Now for an element, it's whatever it is on the periodic table based off of its elemental formula. I'm going to come back to oxygen. So if we look at sulfur, sulfur on your periodic table is number 16. The mass at the bottom is that 32.07, and the unit for molar mass is that's how many grams are per mole of that substance. So if we have 1 mole of sulfur, if we put it on a scale, it's going to be 32.07 grams. So I wanted to come back to oxygen for a reason. So oxygen is number 8. The mass listed on the periodic table for oxygen is 16 grams per mole. However, remember oxygen is one of those elements in Brinkelhoff that is diatomic. So you're never just going to have one oxygen floating around by itself. It always has to be attached to something. So remember, if we have elemental oxygen or oxygen gas, that is O2. So since there's 2 oxygens in elemental oxygen, we would have to multiply that mass by 2. So the molar mass of oxygen gas that we would breathe is actually going to be 32 grams per mole. So beware of those diatomic molecules that can kind of sneak up on you. So remember, anything in Brinkelhoff, whenever it's an element by itself, there are always 2 of those atoms that make up that molecule. So I just wanted to kind of warn you of that because that does come up from time to time. And since this mass, this molar mass, is equal to 1 mole, that is also equal to Avogadro's number. So this is the mass of 6.02 times 10 to the 23rd particles. So they're all kind of equal to one another. So looking at a couple, and we're not going to do all of them. So let's look at these first two. What's the molar mass of the following? And half the battle is going to be finding it on the periodic table. So making sure that you're familiar with where stuff is. So I want someone to look up neon, and this one also look up chlorine. So can anyone find neon and tell me what's the mass of neon on the periodic table? JJ.
20.180.
Yeah. So 20.180. And the unit for molar mass is always going to be that grams per mole. So that would be the molar mass of neon. It's just looking it up and making sure to add that unit on there that it's grams per mole. All right, what about chlorine? You want to find chlorine?
35.
Yep, Ollie said 35.45. Here's where I wanted to do chlorine specifically, because remember Brinkelhoff includes chlorine. So remember, whenever it's by itself, it should be Cl2. So if we double the 35.45, it's going to be 70.90 grams per mole. So it's remembering which ones are in Brinkelhoff, and if they're by themselves, you have to double them. So I wanted to have that one as an example just for that purpose, because those will kind of sneak up on you from time to time. So y'all feel okay with molar mass of an element? Good, okay. So let's look at what if we don't have an element, what if we have a compound? So looking at the mass of a mole of a compound, so molar mass of a compound. In order to find the mass of a compound, we first have to know its formula, because we have to know how many of each element we have in that substance. So up here I have the example of sulfur trioxide. So remember, sulfur is S. It's sulfur and oxygen are nonmetals. So remember that prefix tri tells us that there's going to be 3 oxygens. So the formula is SO3. That should be a subscript. It undid my subscript when I copied it over. So whenever we're trying to find the mass of a compound, we are simply going to add up the masses of all the atoms in that compound. So this is why we need the formula. So whenever we're looking at sulfur trioxide, we have 1 sulfur, because there's no subscript on sulfur, but we have 3 oxygens. So anytime you have more than 1 atom, you have to multiply by that subscript. So whenever we're finding the mass of this, we have 1 times the mass of sulfur. Our periodic table says 32.07. Other periodic tables might say 0.06, depending on which one you look at. Plus, we have to multiply the mass of oxygen, and we are doing the atom oxygen, not the element oxygen that's diatomic. So remember, it's only diatomic when it's by itself, not when it's in a compound. So we have to multiply oxygen to 16 by 3, since there's 3 of them. And whenever we add them together, we're going to get an overall mass of 80.06 grams per mole. Excuse me. So elements, we just had to look straight on the periodic table. And then remember, if it was diatomic, we had to double it. For compounds, we're having to add all the atoms together to get the overall molar mass. So let's look at a couple of these together. So let's look at this one, where we're going to find the molar mass of glucose. And anything that is kind of a common name or something like that, I'll give you the formula for. So you don't have to know like organic things or anything like that. So glucose, the formula for it is C6H12O6. So whenever we break this down to do molar mass, we're going to have 6 carbons plus 12 hydrogens plus 6 oxygens. So that's kind of our breakdown we're going to do finding molar mass. So can anyone find the mass of carbon? Yeah, so 12.01. Plus we have 12 times the mass of hydrogen. Does anyone find hydrogen? Yeah, 1.008. And then plus 6 times, what's the mass of oxygen? Yeah, 16. So that's kind of filling in all of those masses off the periodic table. And then we just need to add them together. So you should get 180.156. And remember, molar mass is grams per mole. Now let me know if I typed in something crazy. That does happen from time to time. So not terrible. Okay. All right, I do want to do one more finding the molar mass because I wanted to show you what kind of happens when you have that polyatomic ion in there. Okay. So let's look at this one. If you're following along on the notes, I did change what the substance was. So I changed it from silver nitrate to cadmium nitrate. So here it wants us to find the molar mass of cadmium nitrate, but it did not give us the formula. So this is where those nomenclature scales come in. Cadmium on your periodic table is CD. That was one of the ones that was always that positive 2 charge. It's in that group 2B in the transition metals. And then nitrates. Remember, anytime there's an ATE, it's on your polyatomic list, which is on the back of your reference sheet. So nitrate is NO3 negative. And then remember, we had to crisscross our charges because we have a metal and then an anion. So cadmium is going to have a subscript of 1. Nitrate is going to crisscross over and get that subscript of 2. So remember, we had to put the nitrate in parentheses so it doesn't look like we have 32 oxygens. So I wanted to show you this one specifically because we have a polyatomic ion with a subscript on the outside. So what's going to happen is that subscript is going to distribute to everything inside of parentheses. So whenever we look at what masses we need, we still have 1 cadmium. That didn't change. But there's 1 nitrogen and nitrate, but that 2 on the outside multiplies by the subscript of 1. So we're actually going to have 2 nitrogens total once that subscript distributes in. Same thing happens with the oxygen. There's 3 oxygens in nitrate, but the 2 multiplies by the 3 for a total of 6 oxygens. So cadmium's not one that we use too often. That's number 48. So that's 112.41 plus 2 times the mass of nitrogen. So you want to find nitrogen. Common.
14.01.
Yeah, 14.01. And then add to that 6 oxygens. What was the mass of oxygen? Yeah, the 16. So whenever you add those together now, you should get 236.43. And remember, that's grams per mole is the unit on molar mass. So how we're going to use this. So molar mass is going to be our conversion factor to go from mass to molar, mole to mass. So this we can actually set up as a fraction of 236.43 grams per 1 mole. So that is going to be our conversion factor that we're going to end up using. And remember, conversion factors, since they're equal to one another, you can flip them. So sometimes we'll have grams on top, depending on what we're trying to cancel, or we might flip it and have grams on the bottom, depending on what we're trying to cancel. But that molar mass you have to find to be able to change between moles and mass. So this, like I said, is going to be the hardest type of conversion when you're dealing with mass, because it's not a set number. You have to find what number needs to be plugged in. So let's look at how we're going to use these conversion-wise. Okay. All right, so converting between moles and mass or mass to moles. So we're going to use that molar mass of the element or compound as our conversion factor to convert between the mass and moles of a substance. So kind of the same way we've been doing. If it gives us moles, the moles of the molar mass is going to go on the bottom and grams will go on top. And remember, moles is always 1. If we're starting with grams, grams should go on the bottom. So molar mass will go on the bottom. And remember, that's always per 1 mole. So we're just going to flip that factor depending on what we're trying to cancel out. I'm just making sure everybody's with me before we go and do a couple examples. So we're going to do a couple examples together. So let's look at this one. We're going to calculate the mass in grams of 2.50 moles of iron 2 hydroxide. So same kind of process we've been doing. We are looking for mass, and it gives us 2.50 moles of iron 2 hydroxide. So that's what we're going to end up starting with, is that 2.50 moles. Now, anytime mass is involved, you have to find molar mass to plug in some way, shape, or form. So here it does not give us the formula. So this is where we need to use our nomenclature skills to write the formula so we can find molar mass. So iron is Fe. It tells us it's a positive 2 charge. Remember, hydroxide is your base, so that's that polyatomic ion, that's the OH negative. So whenever we crisscross to write our formula, it's going to be Fe with a subscript of 1, and OH is going to get that subscript of 2. So that's going to be our formula that we're dealing with. So we know we're going to have to find molar mass. So iron is 55.85. Add to that, we have 2 oxygens whenever you distribute the 2 in. An oxygen was 16. Add to that, we're also going to have 2 hydrogens once you distribute the 2 in. And hydrogen is 1.008. So if we add that together, our molar mass is going to be 89.866 grams per mole. So now we need to figure out what number goes on top and what number goes on the bottom when we're trying to convert. So since we're trying to get rid of moles and change into mass, since moles is currently on top, where should that go in our next step? On the bottom. And we can change into grams. So remember we said mole is always going to be 1, and that molar mass is going to go with grams. So the 89.866 is going to go on top. So that's going to allow the unit of moles to cancel, leaving us with grams, which is what we're looking for. So we're done. So we just need to multiply these numbers together. And if we do that, we should end up with about 224.665. And remember your unit, that's grams of iron 2 hydroxide. So these conversions take a little bit more time because you have to find that molar mass before you can plug it in, since it's not a set number. And if you rounded differently, like if you rounded your molar mass to 2 decimals or something, as long as your answer is kind of in the ballpark, that's okay. All right, let's do one more together. So this one wants to know how many moles of iron 3 oxide are contained in 92.2 grams of pure iron 3 oxide. And this time it gave you the formula. The Fe2O3 is iron 3 oxide. So we're going to go through the same process. This time we're looking for moles, and it gave us grams. So this time we're going to start with the grams, the 92.2 grams of Fe2O3. since we have mass, we know we need molar mass somewhere. So we can go ahead and find that. For molar mass, we have 2 irons. So it's going to be 2 times mass of iron, which was that 55.85. Add to that 3 oxygens that are 16. So that's going to be a mass of 159.7 grams per mole. So when we set this up, we have grams. So where would that go in our next step? On the bottom. And we can change it into mole. So remember we said mole is always 1. So that molar mass, the grams, goes on the bottom, the 159.7. So that's going to allow grams to cancel. So to solve for moles, we're going to have to do the 92.2 divided by the 159.7. And we should get about 0.577 moles. And make sure to always start with what's given. A lot of people would do, okay, 159.7 divided by the 92.2. But you need to always start with what's given. So you're dividing by that 159.7. So kind of be careful how you type things in. So y'all feeling decent? Okay. So I do have other examples, but I don't think we need to go through them together. I'm going to switch over and kind of show you what you can do on your Part 1 homework. Okay. On your Part 1 homework, wherever you pull it up, you are going to have to do this on a separate sheet of paper. Even if you print it, there's not enough room for you to show your work when you print it. So make sure you can use the sample problems we did in the notes to help you if needed. Make sure to show all work and make sure that every number has a unit. So don't just have random numbers. Always put a unit with it. That way you can make sure you're canceling out units. Whenever you pull this up, so this is going to be due on Friday. So not our normal Thursday, but that's because we're doing some of this tomorrow. And you're going to need a little bit more time to work through those. You guys know how to do set A on the first page. Those are the one-step problems like we just did, dealing with particles and mass. So the first set, 1 through 10, has you going 2 moles, either from atoms or grams. So pay attention to what unit you're starting with. The second and third set are going 2 grams from moles or going to particles from moles. You only know how to do set A, so you only know how to do the first 20. All the others, set B and the second page, are multi-step problems. That's what we're going to get into tomorrow. I will tell you the first page does have answers at the bottom. Now, when we converted this over, it did get rid of some of the negative signs on the exponents. So some of these, like you might get to the negative 22nd, but the answer says to the positive 22nd. It's because some of the negative signs were deleted. But you can kind of use that to check your work. If you get stumped on one, I do have my answer key up here. So you're welcome to try a couple, come check them. If you're getting stumped on one, that's where you can come up and get some help from me. My guys at home, I will stay logged on. So if you're trying a couple of these and you want to check your answer, or you're not sure what you did on a certain problem, we can kind of talk through it. This is all learning the process. So the stuff we're doing now is also going to be used in our next unit as well. So you want to make sure that you're kind of good at these beginning fundamentals before we get to the harder stoichiometry that's using the full chemical reaction. So you guys have the rest of live time. So we have about 10 minutes of live time plus the extra 25 minutes. So you have 35 minutes to kind of work through whatever you can. Like I said, use this time wisely. You're welcome to come check your answer after a couple, just so you make sure you're kind of doing the process correctly before you go and do them all wrong. If you get stuck on something, please come visit me and we can talk through them.